And then after the
So welcome everyone. It's always nice when a student gets to this point where the thesis is ready to be presented and sort of as a closure of a big chapter in your life. And it's really a pleasure to introduce Lauren today. She came to us from Alabama, as I recall, Huntsville, I think, and decided to trade in one small star called the Sun for about 100,000 big, massive stars and 50 galaxies, as it turned out. Although you didn't know at the time, but that's what it turned out to be. And so she's going to tell us today how we can use those stars as traces of dust in galaxies, and then write interesting things about things like dust-to-gas ratio and connection with metallicity's gas in galaxies. Lauren?
Thank you, Renee. I'd like to thank also my committee. Thank you all for coming. Thanks to John Holtzman, Jason Jakowitz, David Bowles. I'd also like to extend some special thanks to the Legis team, especially Lee and Kim, David Dilker, and Janice Lee. And we'll be talking a little bit more about the Legis team a little bit later on. All right, so what is the point of this whole project? What have I spent the last 5 years doing? So first off, I've been generating reddening corrections and extinction maps for nearby galaxies. We're talking maybe about 15 megaparsecs. So for some of you, nearby is very, very far out. For others of you, near 15 megaparsecs, we're talking local neighborhood, essentially. Once we have those extinction maps, you can correlate them with neutral gas maps to constrain dust-to-gas ratios. We'll talk a little bit more about that as we get further in. And finally, we are taking those extinction maps and comparing them with far infrared emission maps of the dust to get a sense of how well we do compared to other metrics. So just a little bit of an outline. First, we'll get into a little bit of background. Then we'll talk a little bit about the data and observations, including the Legis team. And then I'll get into what I actually did with all that data. So first up, what is dust? What are we talking about here? Well, dust is exactly what you think. It's just like the dust that you see blowing around out in Las Cruces now that we're in windy season. It is everywhere in the galaxy, or everywhere in the interstellar medium. You can see in this image here, there's lots of glowy stuff, and then there's these darker regions here. That's the dust. Those aren't voids. That dust is actually blocking the light that we see, and it blocks worse in the optical, or in the blue end of the spectrum and in the UV. Far infrared light does a little bit better, but there's still a little bit of dust there that makes it hard for us to understand what's really going on. In addition to blocking light, dust also emits in the infrared light, and that's how a lot of people choose to measure it. And in addition to all of its effects on light just in general, it also tends to impact star formation. It serves as a catalyst for the formation of molecular hydrogen, which leads to a catalyst for star formation. And that thermal emission that we talked about, that I mentioned earlier in the infrared, tends to heat the gas around it, serving as a feedback mechanism for star formation. And on top of all of that, dust, because it is formed from silicates, carbon, oxygen, nitrogen, it tends to act as a sink for metals within the ISM, therefore impacting a galaxy's chemical evolution. All of these effects combined mean that it makes it hard to understand how a galaxy works as a whole if you don't understand how much dust there is and how it behaves with respect to the rest of the system. So, like I said, one of the primary effects of dust is blocking light. This we refer to as extinction. That equation up there, that's the simple form of the radiative transfer equation for a thin screen of dust in front of a point source. As you can see, there's a wavelength dependence here. It tends to block more in the blue and in the UV than it does in the red. When we talk about extinction, that's just the difference between the observed magnitude of a star and what the actual magnitude of the star is, or how bright, how much light overall is blocked in a specific wavelength. Like I said, there's a wavelength dependence. So because it blocks more in the blue than it does in the red, this also tends to make things look redder than they really are. We refer to that as reddening, and that's just the difference between extinction and two different wavelengths. A typical, what we call, there are different kinds of extinction laws. So the way that dust affects light as a function of wavelength is different depending on what extinction law you apply. For the Milky Way, you see this kind of relation right here. But for other extinction laws, things can change pretty drastically, especially once you get out here into the far ultraviolet. When you're talking optical IR, most laws look pretty close to the same. When we talk about behavior with the dust respect to the rest of the interstellar medium, one of the primary things you talk about is the dust to gas mass ratio. Basically, how much dust there is for a given column density of neutral gas in the galaxy. Dust does require cool conditions to form, so it makes sense that dust would actually be coincident with the neutral gas. In the Milky Way, you see this kind of constant relationship, 5.3 times 10 to the 22nd magnitude per centimeter squared per hydrogen atom. That's a complicated unit, but basically it just means the magnitude of light that's blocked per column density of hydrogen. When you look at other nearby galaxies, though, that relationship isn't always constant. In other galaxies, you can see that there is some variation in the dust-gas ratio. And it turns out that this relationship varies with metallicity. High metallicity galaxies have a high dust-to-gas ratio. Low metallicity galaxies have a low dust-to-gas ratio. The problem is, we don't necessarily understand how that relationship changes with how quickly that relationship changes. You can see there's a lot of scatter here. The relationship, the slope of the relationship is a little uncertain. Logically, it makes sense. If you have a high amount of metals, it's easier for dust to form, so you're going to have more dust. If you don't have a lot of metals, it's harder for dust to form, so you don't have as much. We want to try to nail down exactly how that relationship behaves across a bunch of galaxies. So one of the first things you have to do is measure how much dust there actually is. One of the primary ways people do this is via far infrared emission maps. Dust can be directly observed via IR emission. It's thermal emission, roughly. But because dust can exist at a variety of temperatures and a variety of environments, this relationship, the emission spectrum for dust is very, very wide. You need to measure dust in a variety of different wavelengths. So what we have here is the Andromeda Galaxy in three different wavelength regimes. This is optical, 3-color image. This is 24 micron emission, mid-infrared. This is 160 to 250 micron emission, far infrared. And you can see there is a significant amount of light, and it even changes slightly depending on what wavelength you're looking at. You get a little bit more mid-infrared emission closer to the center of the galaxy here than you do in the far infrared. That's because there's a lot hotter gas, hotter dust in the middle of the galaxy when you get to that point. The other catch is cold dust does not emit a lot, just like your stove doesn't emit a lot of heat when it's cold. Dust, when it's cold, doesn't emit a lot of far infrared emission. So it can be hard to measure that cold dust, and a lot of modeling has to make some assumptions with regard to how much there is. So another way that people use to try to get, especially at this cold dust, is measuring via extinction maps. You take how much extinction there is in a specific location, and you sum it all up, and you build a map based off of that. One of the primary ways people do this in the Milky Way is something called the pair method. You take the known spectrum of some standard star, compare it to the reddened spectrum that you're observing of a star of a similar luminosity class. You compare those spectra, and you can back out the dust spectrum. So you can see this is the reddened star, this is the standard star, and then this is the spectrum of the dust. Pretty easy. This gets difficult at large distances or in very crowded regions. Stars become fainter, making spectra difficult to obtain. Stars get closer together, so neighboring stars tend to pollute the spectrum, and it's hard to isolate those individual stars. A recent work from the Panchromatic Hubble Andromeda Treasury Survey, who I'm going to be calling FAT for the rest of this presentation, has had success with multiband photometry instead of full spectra, but this is still fairly limited, and it's still limited to nearby galaxies, Andromeda. So another way that people use to get at extinction maps is just pure photometry. The FAT team generated this image of the Andromeda galaxy, and they used photometric extinctions and isochrone matching. There is no SED fitting required for this. You don't need a specific. You don't need to know the luminosity class of a star before you try to match the extinction. Instead, they exploit the fact that red giant branch stars exist in the same location on a color magnitude diagram. So they observed a bunch of red giant branch stars, found out that they existed here, whereas all red giant branch stars should exist right here where this orange kind of branch is, and they just back the stars up to match where the theoretical models. This also becomes more difficult in galaxies further than Andromeda. Red giant branch stars tend to be fainter, they tend to be more crowded. You run into all the same problems that you would with pair matching when you start talking about the distances that I'm going to be working with. So just a quick summary here. Extinction maps can immediately be used to correct optical images for extinction. You don't need to convert anything from dust masks or flux. The problem with that is it only measures the foreground dust directly. You have to make some assumptions about the geometry of where that star lies within the disk. You can think about your galaxy as a disk. If your star lies here, you're only going to be seeing, and you're observing from up here, you're only going to be seeing this dust. You have to make some assumption about what dust is down here. It does not require any dust modeling, really. The dust model is instead buried within the extinction laws, which are generally well understood. It does require observations in multiple wavelengths and spectra, just like emission maps. Emission maps, you would need a conversion from dust maps to extinction, which, because of the modeling, isn't necessarily always well known. This does, however, measure the full column density. You don't have to make any assumptions about what the geometry looks like where you can't actually see it because you're just measuring everything. It does require dust modeling and assumptions about the cold dust in particular. It's hard to understand that cold dust unless you can actually see it. So just in general, we're going to be using extinction maps for the rest of this time because they provide a quick look at dust content without needing heavy modeling and can be higher resolution in galaxies outside the Milky Way. All right, so that's kind of in general what I'm doing, or with this kind of things we're talking about. Now, what data did I use to do it? So this is where LEGIS comes in. LEGIS is the Legacy Extragalactic Ultraviolet Survey. It is an HST UV survey of 50 nearby galaxies with a wide range of morphologies, masses, star formation rates, everything, metallicity, etc. They're all within parsecs. And LEGIS has produced color images in 5 bands for all 50 galaxies. We're also using Hubble tools to produce stellar and cluster catalogs, photometric catalogs for each galaxy. The photometric catalogs, we're talking hundreds of thousands, sometimes even 1 million stars per galaxy here. And the cluster catalogs are just as expensive in some cases. Current progress, all the observations are complete. They're all publicly available on legis.stsci.edu. Yes, those are Legos in the L. So this is just a quick collage of all of the LEGIS galaxies. This image is organized by Hubble type with earliest types at the top, all the way down to the bottom late type galaxies, dwarfs, irregulars, and then by H1 mass on the x-axis. So these are the lowest mass galaxy, or I think it's the other way. Yeah, they're organized by H1 mass on this image. When I started approaching this project, I started out with 5 pilot study galaxies: M74, also known as NGC 628, NGC 6503, NGC 7793, and Holmberg, the dwarf galaxies Holmberg 1 and 2. That represents a pretty good subset of the Legis galaxy range, both in morphology, mass, and distance in particular. M74 is at one of the furthest ends of the Legis sample at 9.9 megaparsecs. NGC 6503 is closer to the middle, about 5.2, and the Holmberg galaxies are at about 3.5 to 4. So this is just an example of one of the Legis fields. This is the central field of NGC 628. You can see I've pulled out subsets of the center galaxy and a star form of the center of the galaxy and a small star forming region. And you can see we can actually pull out individual stars, or at least as close as we can get it. A lot of these may be binary stars, but it turns out that doesn't actually affect things too much when we get to the actual ringing corrections. But you can see we can isolate those individual stars. And because this is a cool image, this is the difference in an H-alpha image of NGC 4490 between ground-based and Hubble. Ground-based is on the left, Hubble is on the right. And you can see we can really isolate individual filaments here that you can't quite get via ground-based. All right, so I also mentioned that we're going to be doing some stuff with the neutral gas. We can't get that with Hubble. So I've had to use existing ground-based data from Things, Little Things, and the Heracles survey. Things and Little Things are H1 surveys for all the galaxies in the local volume legacy survey. A bunch of those galaxies in the Things and Little Things survey that are also in Legis, they're also in the Heracles survey, which is a CO survey. You can't actually measure molecular hydrogen directly, you have to use CO. We use a lot of that Heracles data to round out our data set. And finally, I will need to be using some theoretical stuff, so I used the parsec isochrones. These are the newest set of isochrones from the Padova group. They have masses up to 350 solar masses, though I limit it to about 100 because we're not sure how much we trust anything above 100 solar masses. And they have a very wide metallicity range, from nearly 0 to nearly twice solar. One of the nice things about these isochrones is that you can also tailor them to match your specific photometric system and filter set. And so all the isochrones I've pulled down are tailored to match the HST filters that Legis use. All right, so we have all the data. What did I actually do with it? Well, first things first, we can't do isochrone matching via red giant branch stars, but you can use it using what's called the reddening-free Q parameter. And a reddening-free Q is essentially just a parameter that relies only on the spectral type and choice of extinction law. You don't need to know anything a priori to get a Q value. You don't need to know dust. You just it's just a calculation based off of the observations directly. A lot of formulations for this Q parameter exist. Most use the U, B, and V filters. I'm going to be using the near UV, B, V, and I filters. So this is a plot of T effective, effective temperature of the star versus Q. The blue line is the formulation of Q that I use. The red line is the typical formulation that you see a lot of the times in the literature, including in your textbooks. In this setup, a more negative Q is a more massive star. So we're maxing out at probably around a Q of -2 for that 100 solar mass star. So how do I do this? So like I said, for the isochrone matching, we can't use near red giant branch stars. So what we do, we use massive stars. Like red giant branch stars, all massive stars in a 2-color diagram. So this is V minus I color on the x-axis, near UV minus B color on the Y. All of these stars, once you get above a certain Q, lie in the same location in color space. So we observe a bunch of stars here. These are the red points. All we have to do is back them up with the isochrone where they're supposed to be in a color diagram, using that Q value to guide us. And we can then get the difference between the actual color and the observed color to get our extinction value for that star, using some reddening law. For the rest of this, we'll be using a Milky Way reddening law, which is reasonable for pretty much every galaxy in the sample. So just to prove that it does not depend, so we know based on these diagrams that all of the isochrones lie in the same location for age, but what about metallicity? Turns out that doesn't matter either. So this is, on the left here is solar metallicity. On the middle, there's a Large Magellanic Cloud metallicity. And on the right, it's an SMC metallicity. These two represent roughly the edges of the latest sample when it comes to metallicity range. You can see with this fiducial line here, this black line, that lies in the same location on each plot with respect to the isochrones. So there is no shift when it comes to age or metallicity in these isochrones. So we don't need to know what the metallicity of the star is. We don't need to know how old the star is. All we need to know is its key value. But because this is data, things are messy. These are plots of the magnitude versus error for the LEGAS filter set. This is for the B filter. This is for the near UV filter. And you can see the errors start really climbing out of control right around 24, 25 magnitudes. So in order to guarantee that we're getting the best possible stars, we apply magnitude cuts at 25 in the near UV and 26 in the B in order to limit the effect of photometric errors for our data set. Now, this introduces a very odd systematic effect. Because not all of the LEGAS galaxies lie at the same distance, that magnitude cut is going to change which masses of stars that we can observe in a given galaxy. So these are our 5 pilot galaxies. You can see distance, foreground, extinction from the Milky Way, and these are the maximum observable magnitudes in the near UV filter if no star is extincted at all. And you can see that's different depending on which galaxy it is, which also leads to a difference in our minimum observable mass for stars in each galaxy. Now this gets tricky. We're doing something that involves measuring different regions of the galaxy. We want to be able to ensure that we're getting a similar population of stars across all galaxies in the sample. So because NGC 628 can be considered our worst case galaxy, we apply an additional magnitude cut at -5 in, additional absolute magnitude cut at -5 in the near UV to guarantee that we're only getting stars of 14 solar masses or higher in each galaxy. Now, in NGC 628, that does mean that we're only going to be able to observe a 14 solar mass star if we get lucky and there is no extinction. But once you get above 14 solar masses, you can be reasonably sure that all the stars are relatively close in age. They're really the youngest, most massive stars that you're going to see. So it's a roughly similar population. Obviously, more massive stars are going to you're going to be able to observe extinctions at more massive stars, but that's just the absolute minimum that we can observe. So after we did this extinction correction, we wanted to compare it to some SED fitting models. While I was in the middle of this, the BEAST came out. BEAST is the Fat Teens SED fitting method. It was designed to work with red giant branch stars. And this plot here is a comparison between my extinction correction and the BEAST extinction correction. The black line is just a 1-to-1, and you can see there's some systematic difference here. I tend to overestimate extinction compared to the BEAST, and there's this weird population down here of low mass stars, or BEAST assigned low mass stars, where Beast assigns almost 0 extinction, but I assign some significant value, sometimes up to about 2 magnitudes of extinction, which is a lot. So what's going on? So this is the same plot as on the previous slide. It's isochrone matched extinction versus Beast matched extinction, with the mass of the star colored by the masses of the stars. And then this is that same plot, but the colors now correspond to Q. And just as a reminder, a more negative Q is a more massive star. Beast assigns these stars to be less than 10 solar masses, but the Q that I would assign to those stars would corresponds to a star of 20, 30, 40 solar masses, very high mass stars. So something's going on in here. We're not really sure what it is, but it's likely that because Beast was designed to work with red giant branch stars, and it fits on color magnitude space, not color space, it's likely that there is some photometric equivalence buried within the Beast code that will preferentially choose low mass, low extinction stars against high mass, high extinction stars, just because it's more likely that you're going to be that Beast is going to be able to observe it, so the code preferentially chooses them. That's an area that we still need a little bit more work. All right, so we have extinctions for hundreds of thousands of individual stars in nearly 50 galaxies. What do I do with that? Well, you can spatially bin those stars. You can think about all those stars lie in a certain location in the galaxy, and you spatially bin them, and you can generate extinction maps based on those stars. We calculate average, median, standard deviation, and a maximum. The catch is with the maximum, you don't want to use the maximally extincted star because that's more likely to be your faintest star with your highest photometric error. To try and limit the effect of that error, we instead take the average of the upper quartile in a bin. We require all spatial bins to have at least 10 stars in order to guarantee we're sampling many areas along the line of sight. Again, this goes back to that geometric effect. You can only observe the extinction or the dust that's in front of the star. So you want to try to get as many stars as possible. The more stars you have, the more likely that the average is going to be close to the center of the disk and that the maximum is going to approach the backside of the disk. So this is our 10 arc-second resolution fixed grid map. Each one of those pixels in that grid is 10 arc-seconds big and has at least 10 stars in it. And you can see we do a decent job. We get some of these high areas of extinction where you see those spiral arms that do have those high areas of extinction. There's some increased extinction here in the center. You do see these 2 weird pixels here. That's probably an edge effect over here. As you get closer to the edge of the HST, you start getting a little bit noisier. Toward the edge of the HST CCD, you start getting a little bit noisy. And you can see we get similar good results for other galaxies. You can see there's a little bit of a dust thing here and here. And particularly up here and in that pixel there. Now, for the dwarfs, like NGC 5253, the extinction is both lower and a little more uniform across the galaxy. For the irregular galaxies, for the bigger galaxies, the spirals, the irregulars, you are able to pick out those individual dust lines pretty well. But that's not great resolution, right? We want to try to do better. We want to try to get as good resolution as possible. But when you increase your resolution, say to 5 arc-seconds, as in this left image here, you also decrease your coverage. You aren't able to see extinction in a lot of these areas of the galaxy because there just aren't that many stars. Stars aren't uniformly distributed. Well, maybe we can exploit that non-uniform distribution and do an adaptive resolution map. So the idea behind this is, in areas where you have a high number of stars, you can get away with having spatial bins as small as 1 arc-second. But in areas where you don't have a lot of stars, like this outer edge or even in this gap right here, you want to increase your bin size to get as many stars as possible. So in this adaptive resolution map, each arc second, we look for 10 stars within a radius of an arc second. If you don't find those 10 stars, you make the pixel bigger, you make your search area bigger, up to 2 arc seconds, then 5, then 10. If you don't have if you don't have 10 stars within 10 arc seconds, you just ignore that pixel, say it's not there, or say there's no data for that pixel. But you can see we do a lot better here. So here on the right is the adaptive resolution map. On the left is a contour with contours at 20, 40, 60, and 80% of the maximum observed extinction for that map. And you can see we do a lot better. We are able to trace these spiral arms pretty well. So there's this gap here where you don't really see any extinction. And especially in the center, you're able to really pick out those areas of high extinction in the dusty center lanes. And you do pretty well for these other galaxies. Again, in the dwarfs, things are lower and a little more uniform. In this irregular galaxy in particular, we are able to really pick out these little tiny individual filaments in those areas. All right, so we have the maps. What do we do with them? Well, we said one of the most important things you need to learn is how that dust behaves with respect to the neutral gas. So you do dust-to-gas ratios, dust-to-gas correlations. You want to try, however, to match resolutions as best as possible, and most infrared emission maps have resolutions of about 10, 15 arc seconds. So you actually don't need the adaptive resolution maps for this. You can use those 10 arc second maps. So we take those 10 arc second maps with pixels that have at least 10 stars, compare them to the neutral gas maps, and you can then measure your dust-to-gas ratio just with a simple division. Again, just as a reminder, the observed Milky Way relationship is about 5.3 times 10 to the 22nd. And this should be similar for all galaxies that are Milky Way-like. Similar metallicity, similar morphology. The catch is, our average maps, remember, are probably only observing about half the dust in a given region. So the observed relationship that we should find is about 2.65 times 10 to the minus 22. This, again, should hold for galaxies similar to the Milky Way. This is what we observe. So each of these points, on the x-axis of all these plots is the extinction in the B band, AB. On the y-axis is the neutral gas column density. For each of these points is a pixel in the neutral gas, or in the extinction map, in that 10 arc second extinction map. Blue points are for the average map, red points are for the maximum map. And you can see there is a lot of scatter. It's hard to observe these things. And some of that may be geometric effects. We could be observing stars at different lines of sight. Different areas could have different metallicities, which gives you a different dust-to-gas ratio. We'll get to that a little bit more in a second. But you can see everything, NGC 628, looks like it might fall in that same location. So these lines here, the solid one is the full dust-to-gas ratio from the Milky Way. This dash line is the half relationship. But in general, it looks like a mess. We think there might be some geometric effects, so what if we average it over some area? Things look a little more reasonable. So on the right here is a plot of NGC 628 divided into radial bins. So each one of those points is some radial bin of NGC 628, and it's the dust-to-gas ratio against the galactocentric radius. And you see something similar in NGC 5457 once you expand past our pilot sample. These two galaxies were big enough that we were able to expand into radial bins. Some of the other galaxies, we just simply take an average over the entire galaxy. Well, you see that things look a little bit more well-behaved, but why is there this gradient? Why are we decreasing the dust-to-gas ratio with respect to radius? Well, it goes back to that difference with metallicity. So this is the metallicity versus the dust-to-gas ratio, or log of the dust-to-gas ratio For all of the galaxies in the latest sample that I was able to generate extinction maps for and that had available neutral gas map data. For some of the galaxies, like NGC 628, NGC 5457, and M51, I was able to generate dust-to-gas ratios in radial bins. So you can see NGC 628 here, 5457 here, and M51 here. Now, with the exception of N51, most of the galaxies show a reasonable distribution, a reasonable positive correlation with metallicity. M51 is very weird. M51 is also an interacting galaxy, so there are weird things that are going to happen with that one. So we have this relationship. How does that relationship, or what kind of fitting can we do to that relationship? So here you see the gray line from Remy Royer et al. 2014. They did another dust-to-gas ratio study using far infrared emission maps. This black line here is a single power law fit based on the 5 pilot galaxies. Those 5 pilot galaxies, just a reminder, were NGC 628, 6503, 7793, and the 2 dwarf galaxies, Holmberg 1 and 2. You can see our pilot sample has a slope that is a little bit shallower than the Remy relationship, but because of geometric effects, where you might observe lower extinction in areas of high extinction just because of our selection effects, these higher metallicity, high extincted, high dust-to-gas ratio galaxies may actually be slightly underestimated, meaning they're going to be pushed up. And these low dust-to-gas ratio galaxies, low metallicity, also may have been overestimated because of the effects of the CO to H2 conversion factor. It's been shown that that has some variation with metallicity. I used a constant ratio, but if you use that varied metallicity relationship, some of these galaxies may actually fall down to right about here, which would bring them in line with the single power law, and even decrease that slope, or increase that slope. This red line here is the fit to the entire sample of galaxies that I was able to do this for. Again, it's shallower than the Remy Royer, but for the same reasons, it could be steeper than what we observed. But Remy Royer didn't just do a single power law. They also had this broken power law, which is this dot dash gray line right here. My broken power law is this red line here. And it's driven primarily by the fact that these low metallicity galaxies have very high dust-to-gas ratios compared to what you might have seen from Remy Royer. Again, it's possible these are overestimated, which might bring this more in line with the Remy Royer relationship. But as it stands, this relationship is drastically different from the Remy Royer relationship. Part of that is Remy Royer used a fixed slope for their high metallicity end, which means our fitted slope may be wildly different. Also, Remy Royer went to about 7.6 in metallicity, whereas I'm locked in at about 7.8. It's possible with more observation, some of these, this knot here may shift further out. It's possible, it's just hard for us to reproduce that same one. But we did pretty well with what we've got. All right, so time to discuss M51. It's very weird. You can see there's this merging galaxy up here. This is a plot of galactocentric radius versus dust-to-gas ratio. These are the same bins that you saw in the other plot. This blue line here shows the full field of both galaxies together. This red line shows the dust-to-gas ratio without the companion galaxy included. And you can see that it gets rid of some of that increase at the outer radii, but it's still relatively flat, which is incredibly weird. Fortunately, everyone else is seeing the same incredibly weird things. There are other studies with far infrared maps that show this same dust-to-gas ratio gradient. They show a low, fairly flat, but not non-existent metallicity gradient as well, which might help out with some of that. But the interaction here, we think, is really what's driving the problem. All right, so how do we know that any of this is worth anything? How do we know that it is actually correct? Fortunately, there is a team called the Kingfish team. They are currently building infrared maps of many of the same galaxies that are in the Lega sample. They released a preliminary map for NGC 628. These maps use so as a reminder, the emission maps require a lot of modeling. A lot of early simple models use some kind of modified black-body relationship to account for some thermal emission. But most use a more complicated model from Drain and Lean that takes into account effects from emission lines, polycyclic aromatic hydrocarbons, PAHs, which could be a thesis all in of itself. It has been. But this more complicated model has had issues, but our adaptive resolution maps should be able to trace a lot of the same large-scale structure that you see in these regions with many stars. The FAT team found that these maps maps built from the Drain and Lean model tend to underpredict dust column densities compared to the extinction maps by about a factor of 2. And they tie it back to a lot of that cold dust that we don't necessarily well understand. So qualitatively, we should be able to reproduce a lot of the large-scale structure. Quantitatively, we should be able to reproduce this factor of 2 difference, at least for NGC 628, where it has that map. So what we have, this is a Spire resolution map from Agnano et al. 2012. And these contours are the same contours that we used earlier in the central field for NGC 628. You can see we are able to trace that general structure. There are a few regions here that show the highest extinction in the areas that show not the highest emission. But a lot of that may be a possible resolution effect. We're able to trace a lot of these tiny filaments that might get smeared out in the lower resolution IR emission maps. What about quantitatively? Again, you can break those near far infrared emission maps into the same radial bins that we use for the extinction maps, and then calculate some average dust to gas ratio for each bin based on both maps. So this is metallicity. This is the dust to gas ratio for the infrared over the dust to gas ratio for the extinction. And you can see that this line here is it just marks a factor of 2 difference. And you can see we're a little bit lower. Our average is about 1.5, but given some of our systematic effects that we have buried within our analysis, we're still pretty close. That central bin, that outer bin at the lowest metallicity is very low. It's possible that we're starting to lose some stars. It's possible that we're just lacking enough data in that outer bin to be able to really pull it off. All right, so what all did I do? I generated reddening corrections and extinction maps for nearly 40 galaxies of the Lega sample. There were some galaxies that were a little too far away or too heavily foreground extincted that I could generate that. I didn't show all 30 galaxies. If you want to see all of them, you just check out the thesis. In general, you find lower extinctions in dwarfs compared to the large spiral and irregular galaxies. And systematic differences between SED fitting and isochrone matching methods exist. It's possible that has to do with how the beast code was constructed. I also correlated about 10 extinction maps with neutral gas maps to determine dust to gas ratios for those galaxies. You do see a large scatter between pixels, but if you do spatial averages, you do a lot better. You can then find a broken power law relationship between dust to gas ratio and metallicity. For galaxies with available dust maps, I then compared the extinction maps with the IR emission maps, at least for NGC 628. The Kingfish team is actually working on an updated model working on more maps using an updated model from Drain and Lee. Dust to gas ratios in NUC 628 showed a difference of about 1.5 between the maximum emission map and the far infrared map. But with these new maps from Kingfish, we'll be able to really get into, is that consistent across all galaxies? Are we really similarly across all of these galaxies regardless of distance? So, future work. With all of these maps, with all of these things that I created, you can explore variations of the dust to gas ratio with things other than megalicity. We have a wide variety of galaxy morphologies and star formation rates in the latest sample. You can really get into maybe why some of that scatter exists on some of the existing literature plots. Further, you can explore systematic differences between SED fitting and isochrone mapping. The Beast code is open source, so anyone can run it. Anyone can try to match their extensions using those isochrones. You can also correlate these adaptive resolution maps to H-alpha emission maps, basically to study differences in extinction between the BIG and H2. This is an area of active study, and it's sometimes difficult to get extinction values for those H-alpha maps. Most studies use H-beta, the ratio of H-beta to H-alpha. This you would need to get those H-alpha or H-beta images at all. Finally, like I said, you can compare these extinction maps to the Kingfish far infrared emission maps for other galaxies. There's about 10 to 15 about 15 galaxies in the Lega sample that are also in the Kingfish sample, so you can really get into those differences there as well. So that's all I had. Thank you, and I'll take any questions.
So when you look at pictures of galaxies, you see dust, and sometimes those dust is pretty filament. So what's the kind of sort of spatial scale effect and what stars? I don't know, it's very filamented.
Yeah. So the spatial scale of dust is actually bigger than stars. So you do see that filamentary structure, and with the adaptive resolution maps, you can start reproducing that a little bit. But with the stars that we're able to observe, you're not going to. So there are stars that are going to be buried in those high molecular gas regions that are going to really get at super high column densities of dust. With what we're observing, it's a little more diffuse, so it's less of a problem.
You worry about fire numbers starting missing. You said there was very lot of
So yeah, you're going to have things that are buried in the arm a little bit, but when you're talking those 10 arc-second pixel maps, as we average it out, it's okay.
I mean, there are regions we don't see where there's a lot of dust using that. I mean, that's selection effect. So you have to.
But even without that selection effect, like imaginary, you could have not like this imaginary coverage factor. In some cases, with dust, maybe there's only 2% coverage factor. You couldn't hit it. Then you would start.
Right. Although at some level, massive stars do happen in places where dust is likely to be present. But it's the hardest part is you don't see the highest extinction. So at some level, you could sort of say all these dust to gas ratios are low. That's how you could try to interpret the data, and so in a way, it's sort of amazing that it works as well as it does. Yes.
So, just out of curiosity, because one of the systematic differences between the SED and the have you considered how well-lit clusters might affect that? Or when you're looking at the star counts, to consider the biases that can be introduced from well-lit clusters versus consider
Yeah, so Lattice actually has built cluster catalogs as well. And all of the catalogs used in the extinction maps are matched against the cluster catalog. So theoretically, all the clusters should be taken out.
I have a question for you. You showed this Galaxies plot. How different is gas sample from the And what were the lines in that plot?
So Remy Rouet used most of the Galaxies points as well as their own.
And the lines in the Galaxies plot, were those the Remy Rouet lines?
No, Remy Rouet hadn't acted.
Okay, so I'm just curious where those lines would fall in with them.
Yeah, I did not put that in there. I think Remy Rouet was actually similar to the Galaxies. If I recall.
Because that goes to 7 in that 3, you cut out at 7.8, so
Yeah.
we start at 7.8. And then I guess you didn't plot dust to gas, but you plotted AB,
Yes.
H1, so it's not immediately clear where. I mean, it might be worth actually converting the point to that. Okay, any questions, John?
That's the pictures of that.
Pretty good.
I mean, but you say, oh, I measured my maximum, they might be. Use the picture, that's the picture, divided by the continuum picture. Measure that.
So I think.
You need an infrared like Ivan. You want a pure starlight, K-band.
So I think the problem there is you're going to be getting different populations of stars. So if you're looking at the blue, you're going to be looking at mostly massive stars. Whereas if you're looking in infrared, you're going to be getting mostly like giant red stars, low mass stars. Even some contamination from the early bits of the dust. So I think it's more complicated than just taking the images and providing them. Right? You're going to be looking at different sources. With different sources. Yeah.
I was going to say that it sounds a lot like what we're doing. So, in F31, 32 years ago, 35 years ago, something like so I have photographic plates, right, that were calibrated in PVR, and I did exactly that. I took, but not with infrared data, which didn't exist, but just, hey, can I see the dust lanes in the galaxy? Can I actually not estimate what the light should be there? Okay, and then get extinction. And so there you can use a nice trick for M31 of physics orientation. You can compare near and far sight. I'm assuming the galaxy is symmetric between near and far. So you just measure the light on the other side, and you say that should be seen on the near side, and what is this difference? And so then I did that, especially where the bulge is, etc. And you could test the galactic extinction law with the RD of 3.1. I did the dust to gas ratio, and there was also something strange that popped up which showed there was scattered light that wasn't accounted for. That's the other thing. If you do diffuse dust, when you do dust lane stuff, you have to look at light scattered. Whereas here, when you do sterile features, you don't get that stuff. But so it's not impossible. You could do interesting things with that. But it would take some thinking, like how do you take those H16 units and just do that? What do you use as an approximation for what the light should be? And geometry numbers too, so that it's still under the total attention. Geometry and very. Okay, yes.
I have a question about the proton follow-up. Yeah, so is there a physical implication as to why you should do a proton follow-up and something like right? Or is it just a statistical fit?
It's just a statistical fit. Not really sure. It's possible there's a different correlation mechanism for the dust when you start getting to low middle sea galaxies. But we're not.
I mean, it's a relevant question because you didn't have much time to talk about this extract. You calibrate CO and molecular gas. So this is done assuming a constant extract, where you could reduce the effect of that golden power law by increasing the gas column density for those leftmost points, i.e. assuming that the conversion of CO observations to molecular gas should be a different factor and in the direction that people think it goes. And so that would lower the leftmost points and make it somewhat less of a golden power. But threshold effects are seen, so it's possible that there is, if that's not the explanation, it could be that there is a real information that's really changing some at risk when you destroy them.